Hi Year 12, welcome to our next video on vectors. The first thing we're going to have a look at today is the magnitude of a vector, and that will match up with 305 in our Maths in Focus textbook. But before we do that, I just want to note that we have a section on our HSC formula sheet which is on vectors. So if you have a look at the last page of your HSC formula sheet, and I've just snipped it over here, here's the section on vectors and the formulas that we end up with. So we're going to use this top one today. We'll use this second one next week, and we haven't really looked at what these bottom two are in having double vectors, but we can see here, and I think this is a really handy one to note, that if we have a vector, x goes with the I and y goes with the j component of that vector. So that's something that you don't need to memorize. But we're going to look at this first one today, which is called the magnitude of a vector. Let's have a look over here. So a vector can be written xy, and that's the position vector. Remember, a position vector starts at the origin and goes to that point xy, and that's the name of that vector, and that would be this vector over here on our graph. So starting at 0, going out to this point up here, which is xy, and we can call that vector xy in its column format. Now what you will notice, which is something that I think a couple of you picked up in a lesson last week, that if we have a position vector, it has an x and a y component, and we can use Pythagoras' theorem. So remember back in year 8, I think it was, the rule said that if we have an x and a y and we have a hypotenuse, we'd have x squared plus y squared is that hypotenuse squared. And if we take the square root of that hypotenuse, that would be the square root of x squared plus y squared, and that would give us that hypotenuse in length. And that's called the magnitude of our vector. So we write the magnitude of a vector, or the size of a vector, or how big our vector is, as the square root of the x squared plus the y squared. And that's our x and y on that diagram over there. And that formula is given to us in our HSC formula sheet. So a nice easy one. So in this case, we're assuming, because we are only still looking at the easy things, that we're finding the magnitude of the following vectors, that we would have a right angle between the x and the y component. So I'm telling you that in these two questions we do, so the rule would work, but we can look at that down the track to make sure that there is a right angle in there. So if I'm given a position vector v that is minus 3 and 4, the magnitude of that vector would be the square root of minus 3 squared plus 4 squared. Noting that when we square a negative, the negative itself is squared to become a positive. So we end up with 9 plus 16, which is the square root of 25, which is 5. So a nice simple one. The magnitude of that vector is 5. Similarly, we can do the same with 2 and 7. If we're taking the square root of each of those squared, we add them together, we're going to end up with 7.3. It's done that to one decimal place. So those are fairly straightforward. Now what we can have a look at here is the next style of question, which is saying find the exact magnitude of vector AB. Now exact, we know, means it is in generally left in a surd form, and we're not copying it into a decimal form. So if we were to draw those two vectors, OA and OB, in this case I'm letting you know that there is a right angle between them. We can work that out. But in this case we do have a right angle between A and B. We can use Pythagoras' theorem to find the distance or the magnitude of AB. Now noting that the difference in the rule is to get our length of this vector here, we're looking at x, change in our x values, and then we're looking at the change in our y values to get that. So the change in our x values is between 1 and 3, because we've moved from 3 down to 1, and that gets us that distance in there, and we square it, and our change in our y values. Popping that in, we'll end up with an exact value of 4 times 5, which is root 20. Root 20, which is the square root of 4 times 5. And we take that out the front as a 2. So we're looking at a surd. That's a simplified surd answer. And we can do the same with the other one over here. And I'm not going to work that one out because that's written there for us. Okay. The other thing we want to have a look at today is unit vectors. So a unit vector has the same direction as the vector that we're looking at, but it is of size 1. So to distinguish from other vectors, we add a little hat or a little top to the vector, and we call that u hat. So in this case, if our vector u is this distance and it has a magnitude of u, and we can work that out in a moment, our unit vector up here has a little hat on it, and it has a magnitude of 1. So for example, I've drawn here our vector u, and I've said that the vector u is 2 units long, and I'm going to pop little magnitudes along there. Okay, if it's 2 units long, the unit vector that relates back to that vector would sit on that vector, it would be parallel to that vector, or it wouldn't have to sit on it, but the position vector would sit on it if they were both position vectors. It could sit next to it and be 1 unit long, but it would be parallel to that vector, and it would be 1 unit. So in this case, it would be half the length of the 2 unit vector. So unit vectors can be either a position vector or a displacement vector. Remembering, if we want to write that vector in a form of a column vector, we need to move it back to a position vector. To find the unit vector, we divide the vector by the magnitude. And here's our formula. So the unit vector, which is the little hat here, is the actual vector divided by the magnitude of that vector. And you can write it in this format as well. But generally, we use that first format. Highlighted that there for us. That is not given to us on our HSC formula sheet. So our unit vector is our vector divided by the magnitude of that vector. So let's find the unit vectors for each of the following. So if my vector u is 2i plus 3j, noting we can also write that as the vector 2, 3. I'll pop that in there for us. That's also our vector there. Then the unit vector would be our vector divided by its magnitude. Let's look at the magnitude first. So the magnitude would be our x component plus squared plus our y component squared. Simplify that to root 13. So our unit vector is our original vector, and each part of that is divided by our magnitude of our vector. And we can do the same with the next one, and similarly with the last one. So I'll get you guys to work through those. We just need to use our formula, work out what our magnitude is, and divide our original vector components by the magnitude, and that will allow us to get our unit vector. Noting that in our last one here, when we do that, I can simplify my 2 components into its simplest form. Okay, the next vector question is a show that question. So you wanted to show that vector u, which is 1 on root 2i plus 1 on root 2j, is a unit vector. So showing means you need to show your evidence, and we want to have a look at showing it's a unit vector. So let's just think, well, how do I show things are a unit vector? So I would be putting down my definition of a unit vector, which is the unit vector u is equal to my vector u divided by the magnitude of my vector. So let's pop everything into that and see what we end up with. So the magnitude of my vector u over here is the square root of 1 over root 2 plus the square root, it is 1 over root 2 squared plus 1 over root 2 squared. When we square each of those, we get a half. Adding the half and taking a square root, we get 1. So that is saying that the magnitude of my vector is equal to 1. If the magnitude of my vector is equal to 1, then it is a unit vector by definition. So that one's done. That one's fairly easy. Now let's have a look at the final example for today. Find the vector that is parallel to the vector u, 3, 2, and has a magnitude of 5. Now, I think we need to draw this diagram first over here. So I pop that over here. And what I've got there is my green vector, vector u, is 3 and 2. So that's the green one up there. And what I'm thinking, if I want to show that a vector is parallel to that vector, if it just sits along that vector and becomes bigger or smaller, and it's a position vector, then it's going to be parallel to vector u. So if I wanted a vector that is vector size 5, what I could do is shrink down my vector u to become a unit vector, so it's size 1, and then multiply that by 5, back up to the pink vector, which is 5 units long. And that's what I would like to do. So I'm going from green down to blue and up to pink. So we'll let v be our vector that we're going to eventually find, but we're going to have a look at the unit vector, the blue one. So the unit vector u, which is this little one over here, remember, is equal to my vector u divided by the magnitude. So the magnitude of that vector u, and there it is, 3, 2, is 3 squared plus 2 squared, which is the square root of 9 plus 4, which is root 13. So my unit vector u is equal to my vector divided by that root 13, so it's 3 over root 13, 2 over root 13 in a column vector format. So that's what that little blue vector looks like there. Okay, and now we want to, and we know that that is parallel to our original vector, but we now want to find that parallel vector that has a magnitude of 5, and that's going to be our pink one over there. So we're going to size that one up to be 5 times the unit vector. So I'm going to times this unit vector down here by 5. I've written that down below. So my new vector v is 5 times. So v is 5 times my unit vector. V is 5 times each of those parts in my column vector. So I get 15 on root 13 and 10 on root 13, which I can write as components I and j as well if I like. And that's the solution. The only other thing I want to add in there for my notes is that if we were finding the direction of a vector, what we want to think of is basically our a coordinate plane, but we're looking at 0 and moving around to 90, 180 and 270. So if I had my vector here OA, if I wanted to find the direction that it sat in, we would be starting from this point here at 0, but thinking of the 0 degree line, or the x-axis, being our 0 point. So my degrees for that vector would be 90 plus whatever angle that is in there. And I can find that angle in there using my m, which is rise over run, which equals tan theta. So there's a little bit of work I need to do, but I can do that based on my maths from year 9 and 10. So if, for example, my point A was 2 and 2, for example, then I'll be working in this triangle here, and my theta I'd find from m is equal to tan theta is rise over run. Well, my rise is my y value, so I've got 2, and I've got 2 as my run. So tan of theta is 1, so theta is 45 degrees. And then I would add that to my 180 to get my solution for the angle. So just note that when you're working out your direction, you're starting from 0 degree line and working around that we normally would if we were doing all stations to central.